very excited to have with us today Dr. Pengyu Huang. Dr. Huang is a distinguished scientist with extensive expertise in immuno-oncology, cancer biology, cell biology, and molecular biology. He has a fantastic track record that includes successful IND submissions for both small molecules and immune cell therapies. Currently, as the head of In Vivo Pharmacology at Simcere Zaiming, Dr. Huang leads the preclinical research team with a focus on mouse model development and imaging-based assay design. Before his tenure at Simcere, Dr. Huang guided a team at Minerva Biotechnologies, significantly contributing to the first clinical trial of MUC1 CAR T-cell therapy. In today's talk, Dr. Huang will present a series of innovative in vitro and in vivo studies that are collectively designed to monitor and to evaluate key tumor microenvironment, TEM, cell-cell interactions between cancer cells, immune cells, specifically CAR T cells, and CAF cells, or cancer-associated fibroblasts. It is now with great excitement that I welcome Dr. Huang to present and to explain the results of these innovative studies. Dr. Huang, take it away.
Hello, everyone. So first, I would like to express my gratitude to Dr. Andrew for kind introduction. I also want to thank SII, Spectral Instrument Imaging, for organizing this webinar to give me a chance to share my story. Also, thank everyone joining us. So I think a lot of them, during the lunchtime, I promise I'm going to give the very interesting story, keep you from the hungry. I hope you can learn something from my story. We have the three parts. First, we talk about how development imaging-based in vitro in vivo co-culture platform to recapitulate the large cellular environment of the TME. So this platform allows us can monitor cell-cell interaction between the cancer cells, immune cells, and the CAFs. Second part, I'm going to talk the parallel in vitro in vivo studies. In the last part, I'm going to discussing the rationale and the importance why I using the engineering tumor cell line for this study. Before study, I just introduce some of the ARM-HT. So this ARM-HT is the live imaging you can show here as a blue machine. So with the isoflurane vaporizer system and the EP3 vacuum, so you can do the in vivo imaging. So the right side actually is the picture just take the 2 days before. Actually, it's from the exactly experiment. So you can see the 3 mice, the sleep in the machine. So then the tumor signal be taken from the top, the CCD. Then the imaging show the rat. So in the chamber actually you can put 5 mice in. Also you can put your plate. Actually, it's much sensitive than the plate reader. So first, so we need to pick up the fluorescent protein for the label the CAFs. So you all know, so the in vivo have the background from the human globin. So the cover from 400 nanometer to the 600 nanometer. So if you want to get the better imaging, so you need find some protein from 600 to 800. So the 2015 paper from the Chakdavar group, they give us very useful information. So from this table, you can see based on the signal to the noise ratio, the Katushka 2S have the best number. So this paper also compare between the IRP720 with Katushka about the fluorescence efficacy. You can see a lot filter siding can have greater separation. So in this paper, this suggestion 605 good for the Katushka, and 7675 and 7020 is good for the IRP. But actually, each Army HD have the different filter siting. So I talked with Andrew. His suggestion, we just do the scanning for different filter siting. So here is the in vitro test, and the right side is in vivo. So we using THP1 cell line is immortalized monocytal cell lines. They can be induced to the macrophage. So we overexpression either pKatushka in the top line. Bottom line is the IRP. So the two phagocytors for the pKatushka, you can see top line have the stronger reading, but have the high background. The bottom 5720 and the 6770 have the clear background, even a little bit lower reading. So IRP is really great. So if you separate the background, the reading is linear. So this is very great the data. So in the left side, actually we either injection the cell line in the mouse separately or mix. You see here is mix the pKatushka with IRP. So you can see here in the pKatushka panel, is very great the signal here. So just the signal from the pKatushka channel. So also if you check the IRP panel, also separation well. It's not an overlap or a spillover. So also I want to mention, so the imaging just take 2 seconds. It's good enough. So this is for the fluorescence. So you just put the mouse sleep, then just 2 seconds. Very quick, very common. Okay, before we go to the data, so I want to give a little bit the introduction background about the CAFs. CAFs can protect the tumor against the immune cell. The CAF is cancer-associated fibroblast. Actually, it's one type cell found in the tumor microenvironment. Tumor microenvironment play a very crucial role for the cancer progress. Actually, CAF can do the ECM remodeling, can secrete the pro-tumor signal. Also, CAF can express some immuno checkpoint to against the immune cells, cause the drug resistance. Here is the H&E, the picture. You can see the white yellow head is pointed the tumor cells. The dark yellow head pointed the fibroblast. CAFs is the spindle leg. The bottom is a cartoon. This show the CAFs and the tumor make the complex. This is from the pancreas cancer. You can see also have some ECM here. So in the left side, they show the general idea. So the tumor can recruit the CAF to the tumor microenvironment, then secrete some cytokine and transform the CAF, transfer fibroblasts to the CAFs. So CAFs then remodeling the matrix, also secreting cytokine, then block the immune cell to attack the tumors. Currently, the target the CAFs. So this is the imaging area. A lot of biotech pharma focusing on this area. First, we just want to confirm. So the CAF can really block T cell to kill the tumor or not. So here is a tumor only. Then we put the CAR T. So the very small. You can see here, the CAR T attack the tumor. So then today, the tumor almost be killed off. So if you co-culture with CAFs, the CAFs in the blue color, the tumor in the red color, you can see majority tumor survival. So then actually CAF can protect the tumor, protect the immune cell to kill tumor. So very interesting. So if you culture the tumor with CAF for the longer time, this is 4 days, and then they will make the cluster. You can see the red tumor here, then surrounding by the CAF, they make cluster. So this structure, very interesting. It's very like same as the right side is actually the real tumor tissue standing the calf and tumor. The tumor is purple, then the calf is green. You see the mixed cluster everywhere. Of course, they have the immune cell there. But I just say it's very interesting. The 2D cultures, yeah, some can mimic the 3D, the tumor tissue. So most interesting things, if you culture this cell further, it's 8 days. So you can see that the tumor only is just the flood, but this cup they make the cluster. So because this just happened in the tumor R. The tumor R I will expand more. Is some tumor can resist the immune cell killing. This is a bottom green is just wartime tumor. So here, if you focusing on the cups layer, so you can see the cups just arrange themselves very well on top of the tumor. So they just make the cluster like the spiky balls. So when I saw this picture, so there's a hedgehog and the sea urchin just pump off my head. So you just saw the picture, you can feel the defensive from the spec ball. But here I just want to classify, so I never using this lovely animals. It's not in my iCook, so it's just imaging I put on here. So we already show the CAF can protect the tumor from the immune cell killing. So now I show the live cell imaging. You can see the surrounding the tumor. This is real live cell imaging. The small is the T cell. The red is a tumor. You can see from again. So then the blue cups just surrounding the tumor then protects the killing very well. Okay, so now we already confirm we already have the tumor with CAF. We confirm the CAF can protect the killing in the in vitro. So now we're moving to the in vivo. Here is the experiment setting. I just go through this part. So we have two kinds type tumor group. One is wartime tumor with CAF. The tumor is expression in the luciferase. We can detect it by the luminescence signal. The CAF expression in IRP. So we have the tumor R in another side. So in the individual mice, we gave the dual tumor. So the left side is the tumor only. The right side is one mixed with the CAFs and injection to the mice. So then 12 days after we give the CAR T injection, then we monitor using the MEHT. So in the same time, the same setting, we have the tumor or tumor R with CAF or without CAF. We do the long-term, the in vitro lifestyle imaging. So we capture the imaging from day 0 to day 4, then from the day 8 to day 12. Okay, that goes through the result. First, that's the in vivo. As I mentioned, so we have the two group, bar type and the tumor R. So the imaging have two kinds of imaging. One from the tumor, that's a luciferase based. One is from the CAF, is a fluorescent based. You can see clearly can detect the CAFs. But I also want to mention the CAFs, if not without the tumor, there's no injection, they will die. So they can survive together with the tumor. So then we check the result. So you can see left side is smaller than right side. So means CAFs can enhance tumor growth, also can protect from the killing. So, but in the later on, you can see here, so in some mice, the CAR T is stronger and present. I didn't show the facts here, but actually this might have the stronger CAR T. Then they start to kill the left side, the tumor without CAFs, but the tumor with CAF, they can protect from the killing. So in the right side, so you can see even without the CAFs, because they have the ability to against the killing, so then you can see signal there. But you definitely see in the right side with CAF, the tumor signal is more strong. So then let's see that the CAF can provide the protection for the tumor. So one thing I want to emphasize here, so even this is a radiance number, even the tumor R shows a lower reading, but because we further overexpress some gene in this cell, the luciferase expression low, so then the signal low, but actually tumor is much bigger. So another thing, so this tumor R, you can see they building together. I think they have the more stronger metastasis. So they fusing together. So data just summarized here. So the wild-type tumor, so they can be killed by the CAR T, but with the CAF, so they some protection here. Okay, so then go to the in vitro data. So data a little bit busy. I just go through the structure. So we have the four conditions, just same as the in vivo. We have the tumor, wild-type tumor, the tumor R, this green color and the red color. So we co-culture with the CAFs as red, blue color or without. So treatment is same as the in vivo, the untransfused and the CAR T. So this is one condition we repeat 4 times, the day 4, day 8, and the day 12. The top panel is with all colors. At the bottom, I remove the CAFs and the face. I just focusing on the tumor. You can see the clear signal. So you can see here, the day 8. So just see the without CAF, you can see CAR T can kill the tumor very well, as a mouse be killed. But if you compare the wild-type tumor with CAF, the tumor survival much more than without CAF. It's very clear. But if we focus in the tumor arm, you can see CAF still provide protection for the tumor. So if you see this area, you see the CAF surrounding the tumor. But in the later stage, so you can see the tumor come back, the recurrence. But without CAF, they have much more number than without CAF. But if you compare the wild type with the tumor arm, you see the area look like same there, but actually cells is much different. I will show you next slides. Here is the lifestyle imaging. Start from day 8 after we ate the CAR T. This is wild type with CAF. You can see the tumor size is really big. It's not a lot of cell in the area. I think around 100 cells. But you see the right side, the tumor arm with CAF. It's very dense. I think there's a lot of cells there. So then they spray out the growth. But the wild type, if without CAF, they never come back, never grows. The tumor arm without CAF, because they have ability to against the CAR T, so they come back. But the number much more smaller than the co-culture system. Okay. So then we focusing on the day 8 and the day 12. So because they make the very dense cluster in the tumor with CAF. And the people will wondering the CAF still there or not. But in the day 12, you barely see the blue color. So then I remove the red color. You can see here in the bottle. Actually, the CAFs are there because they just make very dense the cluster with the tumor cells. In the latest stage, you see the blue color is a little bit light, as it means they are not close a lot. But this is just same as the email if you recall the data. So the CAFs, so the co-CAR-T in the tumor, they still there, they live, but they not grow. So the tumor grows and come back. Okay, so we already showed that data. So the CAFs can protect the tumor, the block the CAR-T killing, so that make the protection. So can we the breakthrough this sure? So then we just using the antibody to targeting the CAFs. Actually, it's the CAF marker. You can see here the live cell imaging. After we add the antibody to the co-CAR-T system, the CAFs normal to surrounding with the tumor, so there's no protection. So then allow the CAR-T to kill the tumor. Okay, so now we have the drug. So we want to confirm in the in vivo. So in this time, so we switch, because the proposal I show you is a HEP3B, is a liver tumor with the IMR 90 is a lung calf. I can see this is the calf's legs because they have the marker for the calf, but they are not paired. So now we're using the lung cancer, A549. We're using primary calves. So they have the better calf marker expression in the surface. Also internal in vitro data, so or in vitro team show the better protection. So then we pick up this pair. So this is the in vivo data, just same as the previously. We have the full condition, as CAR-T treatment condition, control condition. We further have the control IgG or the treatment antibodies. So the setting is same. The left side is the tumor only, and the right side is with the HL-CAF2. So the bottom is show the data. So the first is the tumor only. You can see CAR-T is killing the better than the untransfused, but not different between the IgG and the antibody. But very disappointed. So we didn't get positive data here in the co-culture right side. So you see here, IgG control same as the treatment. So then we don't know what's going on. Is antibody not working or something happened? But the good things. So we have the labeling the this primary CAFs. You can see here in the day 0, we see them with the tumor. But in the day 4, the signal almost gone. So actually this cell cannot survive because it's primary CAFs. So actually in the beginning, we start experiment. We have 2 kinds of CAFs. One is the CCD19 loop. So this cell is cell line, it's not primary cells. So we discussing which cell line going to the in vivo. But the in vitro data, the HL-CAFs provide better result. So finally we decided to use this one. But we also try to monitor the cell's growth. But it turns out the cell cannot grow. So then they not provide the protection for the tumor. So then their antibody show no difference. The good thing, so we have the in vivo spectral experiment. Then we found out what is went wrong. Okay, so here just the summary for the part 1, the part 2. So as you see, we successful development the in vitro co-culture system can recapitulate the multicellular element of the tumor microenvironment. So the long-term in vitro co-culture experiment is consistent with the in vivo data. Also, I think we show the CAFs can reshape the tumor morphology that make the cluster. Also, the very interesting things. So this cluster just occurred when the CAFs with the immune resistant tumor cells. So come down to here. We show the tumor arm makes cluster, but we don't know why. So how we investigate the cell-cell interaction just based on cluster is hard to quantify. So we need a better method. We think about that. So also most people, I think they don't want using some kinds of overexpression cell line, engineering cell line. They want a nature cell lines, right? So then I'm going to talk why I using the engineer cell line here. Actually, I struggle a little bit well to get the data to convince the internal group until we saw this picture. So I think this is the most picture today. So I going to spend some time to talk about this. So you see here, so this is green is a 549 cell and with CAF. This is a right side co-culture, but unlike I emphasize the CAFs is outside and surrounding the tumor and protect tumor. Actually, they get in the inside. Very strange, but I'm going to tell you what's happened here. Actually, it's accidentally I got this picture. So then in the beginning, actually, I put the cover slide in the 6-well plate, then seed cell. My purpose is to take this cover slice with the cell, then do the IF staining, then check the like a CAF marker expression or interaction. Actually, this plate is not necessary, no need to keep. But a couple days later, so the immunostaining turned out as no clue and no fault difference. So then I try to throw this plate out. The before throw, I put on the microscopy, and I see that in the hall some cell there, very strange phenotype. After the take picture, then we see very shocking picture that the two cells just naturally, they sort of themselves. The CAF moving to center, then the tumor still outside. So, but the purpose we want to investigate the cell-cell interaction, right? They should supposedly, as expected, they should be working together in the same location. But it turns out that the CAF just moving to inside. So actually, they are not working together for some reason. Okay. So if you put the tumor arm here, you can see here in that hole, the tumor arm moving to inside. Also in the outside, you still see some blue color CAFs there. So one thing I want the mention here, for the wild-type tumor, so if you take out that cover slice, they not moving. But with the CAF, they moving inside better. So then, as most people mentioned, the CAFs can increasing the tumor migration and the metastasis. It's true. But you see the tumor arm without CAF, actually they have stronger ability to move inside. As I mentioned previously, in the in vivo, the two tumors fold them together. Actually, they have the stronger metastasis. If the co-culture, you can see them moving together. So I'm going to show more higher resolution focusing on the corner and the center. You can see here, the tumor are wild type. They grows very well. The most the CAF is gone. Very few of them. This is in the corner. The tumor R, you see, they mix together. So the tumor R have the ability to maintain the tumor there, CAFs there. In the center, you will see majority is CAFs. They're moving to the center. But in the tumor R condition, so they're moving, I think they're moving together. So they're making the cluster just like a first slide show. So then say the CAF tumor R have some ability to working together with CAFs. Okay, because this is a very interesting phenomena. I think maybe most people never see. I just want to talk here again. So in the beginning, so we have the tumor cells. The tumor line is from the ATCG. I think most people using with tumor CAFs. There's also cell lines. They put it in the same plate, 6-well plate. So then, if we take out the center, right? So actually, supposedly they will moving together, but actually not. But the one important thing is that here I do the 6-well plate. I make some space. Then I found out actually they are not working together. But if you do the 96-well plate, so maybe you never see this phenomenon. So in the appearance, so you put the 2 cells in there. So you're thinking they're working together, but actually not. So actually they lose some important factor. So then they cannot working together. So if you put back, just like I did here, I put something back, they call the tumor resistant cell line. So then you take out the cover slice, the mixed space, they working together, they moving together. I think that's a very important information. So if you do some co-culture, so a lot of people also internal, I heard from others, they say, oh, we never see the CAFs to protect the tumor. So then we need to find better CAFs. So from cell line to the primary. But I think the direction is wrong. Actually, it's problems with your tumor cells. Okay, so then I just gave some information about the tumor R. So actually, we just expression some gene in the tumor that makes them to the tumor. So this is just it's not the unique phenomena. Actually, in the 2 cell has a consistent result. The Hep3B, IMR90 pair, also A509 and CC19 pair. So if we give the tumor gene X makes them to the resistant tumor, they will make the cluster. They will against with the CAR-T killing. Also, in the clinical studies, so the CAF marker always correlate with the gene X expression. So if you see the IHC, so you see some tumor has a high gene X expression, you will find the surrounding has a lot of CAFs. So they base the CAF standing. So this is in the clinical, they have the relevance. So the paper from can show the myeloma, CRC or lung adenocarcinoma, they all have this kinds of phenomenon. So the most important things, so this gene X, usually they will lose expression during the transition from the primary culture to the normal culture. So if you take a tumor out, you make cell lines, or you make some kind of PTS model, the gene X will lost. Because the gene X, because they need some tumor microenvironment, cell to stimulate the expression. They need to against the the immune cell. But if you culture them in the single cell culture, so they don't need to protect from the immune cell attack. They now the CAF there, so they don't need that gene to expression. So they just normal cell lines. Here, so I just want to show more imaging data. So actually, I try to understanding the mechanism. Here is tumor R, this green color. The CAF, this is purple. You can see here, after several hours culture, so they will make a cluster. So this imaging captured by Nikon spin disk confocal dress V3. So they show more clear imaging than previously in the InQSat. You can see the make cluster. If you see the face, the mix cluster very well. So in the wild-type tumor, show the right side. So it's just like a normal culture, the two can cell there. I think in most cases you will see this phenomenon. But I just want to emphasize again. So if you want to see the make cluster, they want the immune cell CAF protect tumor from the immune cell killing. You need to put back some gene there. Here's the last video slides. So for visualize the gene X, I fill in the gene X with GIP. Then I do the co-culture. You can see here, this is the tumor cell with the CAFs. You can see the green color, they accumulated just between the two cells. I think they have some kinds of connection between the cells interaction. You see this cell, lovely cell. You can see that it's just like the people they grab the ropes, they climb up. This cell they climb up. So if you bottle this cell line, you see that the cell line just like sit on the slide, then sliding down the slide ball. You see here. So just no matter is the chroma up or the sliding down. Here I just want to mention, so this gene X actually directly played very important role between the cell-cell interaction between the tumor and the CAFs. So they just not say that gene is important for the immune system, although very important for the interaction between the tumor with the CAFs. Based on the data that I show here, that's very important, critical to using the engineered cell lines, the tumor R I show here, to the co-culture system to recapitulate the tumor environment. So this part will offer you a better platform to screen your drug. But I think in the usually, if you're using the normal cell line from ADCC, if you do the co-culture, it's too easy to be killed by your immune cells. So then you move into the in vivo, then you will see different result. So I think there's a gap between the in vitro, in vivo, also maybe from the preclinical to the real human tumor. Because this gene, even in the in vivo, sometimes is not fully expression as the real human tissue. So in that situation, so you need to put this gene back. So then the tumor mimic like a real in vivo tumor. It's just like say like the IPS, right? You need to put back the Yamanaka factor that make the cell actually back to the beginning. So the real ability, the working in the in vivo. This is my point. That's the whole Wagner point is you need some factor back to the tumor that make the tumor is real in vivo tumor. So second part, I think is more important when you do the in vivo or in vitro, if you can visualize the different cell parts. I think mostly in vivo. So if you understand where your CAFs behave, so then you can get the better information. You can easy to troubleshooting, like I show here. So why is the experiment not working? Because there's the HL CAFs not surviving. So that's most important. I think you need a set better in vivo imaging system to trace your multiple different cells. Okay, last part, I will thank you the Zaiming early R&D team and the Simnova team to support me to collect this kind of data and to share with you.